Can you see the screen now?
Yes, ma'am.
Okay, so let's start. So last time I was discussing the fundamental theorem for finitely generated abelian groups, and then I have talked about the invariant factor decomposition and also the elementary factor decomposition. Then I was telling how to go from an invariant factor to elementary factor and vice versa. So I think I have discussed that how to obtain the elementary divisors from invariant factors, right? That I have discussed, right?
Yes, ma'am.
So now we will discuss the other way, that obtaining invariant factors from elementary factors. Obtaining invariant factors from elementary factors. Okay, so let us see how to do that. So you know the elementary factors. So for example, let us consider this group. Okay, suppose elementary divisors of G are given, say 2, 3, 2, 25, 3, 2. That means your G is isomorphic with Z2 cross Z3 cross Z2 cross Z25 cross Z3 cross Z2. Okay. And now you would like to find the invariant factor of decomposition for this corresponding group. So what do you know by the about the invariant factor decomposition? So you know that in that case G will be isomorphic with Z in 1 cross Z in 2 and so on, and there are some relations between these ni's, right? This ni plus 1 divides ni. This property is there for invariant factors. So now, and also what we have observed, we have also observed that all the prime factors of that number should divide the first factor n1. Okay, so then from here, how do I construct these ni's? That is the question now. So you have this group G that is isomorphic with this, and now you would like to find out your n1, n2, n3, and so on, with the property that n3 should divide n2 and n2 should divide n1. So how to do that? So I will first list down what are the primes present in this. So there are three primes are there. One is 2, another one is 3, another one is 5. So there are three primes which are present in this group. So I will list down the primes first. So say p equal to 2 is one, then p equal to 3 is another, and p equal to 5 is another. So you have these three primes, okay? And now we will list down all these primes which are present as what. So for example, how many 2 are present and in what form? So the 2 are 1, 2 and 3, and all of them are present in 2 only, like they are not in 2 square, 2 cube or something. So I will list down all the primes in the order such that the maximum one is in the top and then the remaining ones. So but here all of them are same, so I will have 2, 2, 2. Then 3 is how many times present? 2 times, and they are also present in just one power. So I will list down this 3 and 3, and say 5 is also present once, but that is in not in just single power, it is in 5 square. So I will write down here 25. Okay, and then I will complete this table by appending 1 uh, for the remaining columns. And then from here, what will be the invariant factor? Now, can you guess what will be the invariant factor? Invariant factors will be such that ni plus 1 divides ni, right? So what will be in your n1? N1 will be the largest number, and then I have to choose n2 such that n2 will be a divisor of n1 and so on. So how do I do that? What will be the invariant factors of G?
156 and 2.
You were saying?
156 and 2.
Okay. Yeah. So what I will be doing, I will be just multiplying the elements in the same row together. That's why I have arranged it in the non-ascending order. Okay, means the highest power I have kept. So for example, let me just consider the group to be, say, cross Z5. Okay, I have added one more term and I am trying to find out what is this. So then in that case, I will be having here 5. So 5 is present two times. Okay, once as 25, another time as 5. So I will be writing the uh, elements in the maximum in the top and then the remaining one. Okay, so in that case, what it will be, the invariant factors will be 2, sorry, so n1 will be equal to 2 into 3 into 25. N2 will be equal to 2 into 3 into 5, and your N3 will be equal to 2. So in that case, your G will be isomorphic with Z 150 cross Z 30 cross Z 2. Is this fine? How we are doing this?
Ma'am,
Yes.
actually, I want to ask like there was a question similar like in which we have to there was a question in the test similar like this like we have to
Hmm.
find the isomorphism between two like it was written in same way.
Mm-hmm. Mm-hmm.
So like we have to do that question like with this invariant factors.
You can do that by invariant factor, but as I have not taught you invariant factor till that class test, you can do that without using invariant factor as well.
Okay, and
Okay.
okay ma'am.
Okay, but of course, using invariant factor, it will be much more easier because whatever group is given, you can write down the corresponding invariant factor decomposition for that group. And if you are asked to check whether two groups are isomorphic or not, you just find out the corresponding invariant factor decomposition of the following two groups. And if they have the same invariant factor decomposition, then they will be isomorphic. Otherwise they will not.
Okay ma'am.
I will discuss this type of problem. So basically, now I will say that using the uniqueness statement, we have
Ma'am, could you show previous slide?
invariant factor decomposition.
In previous slide.
Yes, right. We position whatever goes to that and the other. Should I go to the next slide now?
Ma'am, I have not seen till now previous slide.
Oh, is it? Can you see now?
Yes, ma'am. Okay,
Okay.
ma'am.
I
Okay.
think
You
because of
can.
network issues, I guess. Okay.
Yes.
Okay. The uniqueness statement of the fundamental theorem, we can use this process to determine whether any two direct product of finite cyclic groups are isomorphic. So let us consider one example. So I am asking whether Z6 cross Z15 isomorphic to Z10 cross Z9. Okay. Suppose this is the question. So first, how do you see whether these two groups are isomorphic or not? If they are of different order, then you can directly say that they are not isomorphic. But in this case, both of them are having order 90. So both of them are of the same order. So there is a chance that they can be isomorphic. Now let us see what are the elementary factor decomposition for this. Okay. So let us consider Z6 cross Z15. Okay. Now what will be the elementary divisors? What are the elementary divisors for this? Can you tell me what are the elementary divisors for this group?
Z2 cross Z3 cross Z3 cross Z5.
Yeah, so elementary divisors are 2, 3, 3 and 5, right? And it is isomorphic to Z2 cross Z3 cross Z3 cross Z5, right? Now let us consider the other one, Z10 cross Z9. What are the elementary divisors?
2533.
What are the elementary divisors?
259.
259.
2, 5, not 3, 3. Z9 is present. 2, 3 and 9. 2, 5 and 9. Okay. What fact we are using? We are using that if GCD of M and N are 1, then in that case, Zm cross Zn is Zmn. That is what we are using now to find the elementary divisors. So here the elementary divisors are 2, 5 and 9, and it is isomorphic to
Z to Z.
Z2 cross Z5 cross Z9. Now, are they isomorphic? Is this isomorphic?
No, ma'am.
Ma'am, can you repeat once? Like why is it is 3, 2, 5 and
No,
9?
because they are not having the same, yeah, they are not having the same elementary divisors. Okay, here it is 259, whereas it is 2533. Okay, so they have different elementary divisors. So that's why they are not isomorphic. Okay, they doesn't have the same elementary divisors, therefore they are not isomorphic. Is this clear?
Yes, ma'am.
Give me some response if it is not clear or something.
Ma'am, can you repeat once of 259? Like why it is 259?
Okay. So with this, I complete the group theory portion, and if time remains at the end, then I'm planning to give the proof of Sylow's theorem and some more interesting fact, and maybe we can use some software to compute whatever we have learned, like the class equation, or there is a software called gap. Okay, using this you can do various computations in group theory as well. So if there are times, we can go to little bit into the computational direction as well. Okay, let us see.
Ma'am,
So now, yes,
ma'am, can you repeat the 2, 5, and 9 factors? Why I choose?
2, 5, and 9 factors. Why? So how we are, the group is Z10 cross Z9. Okay, and I would like to find the elementary divisors. How do I find the elementary divisors? In the last previous lecture, if you have seen, I have used the fact that if M and N are co-prime, then Zmn is isomorphic with Zn into Zn. So that's why Z10 is isomorphic with Z2 and Z5. From there I am concluding. And Z9, already it is a power of prime. How do I do the, when I write down the elementary factor decomposition, how do I do it? Whatever the
Okay,
primes
ma'am.
are
Okay, I got.
present, you got it? Okay, good, very
Yes, ma'am.
good. Yeah. Okay. Okay, so now let's start today the new topic, that is ring theory. So now if you have understood the group theory, then we will follow the same line of argument for ring theory. But what is the difference between the group theory and ring theory? Whatever properties we have done for group, now we will do the same things for ring as well. But what is a ring? Before that, I need to tell you what is a ring. Okay. Okay, so let's go first. The first example that we have seen for groups, the ring of integers. Okay, so in Z, what we have seen, that it is a group. Okay, it is a group with respect to addition operation, isn't it? We have seen. But apart from addition, there is another operation that is defined on Z. What is that?
Multiplication.
Multiplication. Because if you take two integers and multiply, it is again a binary operation. You are getting again an integer. Okay, so apart from addition, there is another operation which is multiplication. But with respect to multiplication, what are the nice properties? Or may I ask that whether with respect to multiplication Z forms a group? Does it?
No.
Sorry,
No.
Inverse
It
of
doesn't
any
form a
element.
group. Zero.
yeah. Okay, so inverse of an integer, multiplicative inverse of an integer is not there. But before talking about multiplicative inverse, does there exist a multiplicative identity?
Yes, ma'am.
Yes, ma'am. One.
Does there exist a
Yes, ma'am.
multiplicative identity? identity with respect to multiplication? Does that
Yes, ma'am.
exist? Yes, that
Yes,
is
ma'am.
what?
1.
That is 1. The number 1 is the similar to the identity element. Okay. So the only problem here, we don't have the multiplicative inverse. Apart from that, we have this multiplication is associative, identity exists, everything is there. But only that deficiency is there. Okay. So we have two structures. So with these two structures, what we will do, we will try to define a ring. So a ring will be, first of all, should have a group structure. And apart from that, there will be another binary operation with respect to which it will have this other operation will be associative, and identity will, multiplicative identity will also be there. And not only that, there should be some more property, because I have just two operation, addition and multiplication, but they should be compatible. So that property is captured into the distributive law. Okay, so that is also should be satisfied. I will formally define ring. So before that, let us see some more examples. So for here, I am saying that this is a ring. Sorry. So I'm saying that, okay, Z with respect to addition is a group, and with these two operation is having a ring structure, but I have not defined well what is ring. Okay, we know that this is a group with respect to addition, and with multiplication I have the multiplicative identity, and the multiplication is associative. That much we know. What about the rational numbers? In rational numbers, does we have two operations?
Yes,
We
ma'am.
have addition and
And
multiplication. In fact, here the multiplication, with respect to multiplication, every element has inverse also, isn't it?
yes, ma'am.
Yes, ma'am. Be non-zero, no, ma'am.
Every non-zero, of course, every non-zero. Okay, so it is saying something much more stronger than what we need, but anyway, it satisfies what we need at least. So Q with respect to this 2 is good enough. Then real number is also good enough. Okay, now let's little bit go out of this number system. So let's go to MNR. What is MNR? Set of all n cross n matrices. Now I need to have two operations. With respect to one, it should form a group, and with respect to another, it should not form a group, but at least should have multiplicative identity. Can you think of some operations on the set of all n cross n matrices?
Matrix multiplication operation.
Yeah, but I need one operation with respect to it should form a group.
Addition for group.
Yes. So yes. So addition of matrices forms a group, and multiplication of matrices. With respect to this multiplication, I have identity, that is the identity matrix, isn't it? And we already seen that this, with respect to multiplication, this need not form a group, because every matrix doesn't have an inverse with respect to multiplication. So this is one example, another class where we can find two operations. Okay, and now what about this this thing, polynomial ring? So say R is the real number and consider Rx. Does everybody know the polynomial ring?
No,
No.
ma'am.
No, ma'am.
The set of, everybody knows polynomials?
Yes, ma'am.
Yes, ma'am.
Good, good. So what is polynomial Rx? This is the notation to denote the set of all polynomials in X with coefficient from R. Okay. Now, in this set, can we find two operations with respect to which I can, like, with respect to one operation, it should form a group, and with respect to another, we'll have at least the multiplicative identity. Do you know?
Yes, ma'am. Addition and multiplication.
Addition of polynomials. You know how to add two polynomials, right? So,
Yes, ma'am.
addition of polynomials forms a group, and multiplication of polynomial. But with respect to multiplication, does it form a group also?
No, ma'am.
No, because if you have any polynomial, then its inverse need not exist. Okay, and it has
Yes,
the
ma'am.
multiplication has the identity element. What is the identity?
Constant polynomial 1.
Constant polynomial 1. Okay, good. So now you have seen that all these things that I have said, let us say consider one more. So let me just number them. Let us consider CR to be all f from R to R, all functions from R to R such that f is continuous. Okay, so I'm considering all the continuous functions from real line to real line. Okay, can I have two operations on this set CR such that with respect to one it will form a group, and with respect to another it should have at least the multiplicative identity? Can you think of? Can you think of two operations on the set of all continuous functions?
Ma'am, with respect to addition, it is from group, and component-wise multiplication.
Yeah, so I will, how do I define the addition of two continuous function? I will add them pointwise, right? F plus g evaluated at x will be same as f of x plus g of x. That is how I'm defining the addition. Okay, with respect to this, it forms a group. Okay, and I will define the multiplication, that f into g evaluated at x to be pointwise fx into gx. Okay, what will be the identity? What will be the multiplicative identity?
F of x equal to 1.
Yeah,
No, ma'am. Identity mapping. X equal to X.
fx equal to x. Why fx equal to x will
No,
be
ma'am. No, ma'am. No, ma'am. No. 1.
1? Okay, fine. So these are a couple of examples that we have seen. Now let me define properly what do I want to mean by a ring. So through all these examples we have seen some similarity. So then people thought about why to study them individually. Let us study the property all of them are sharing together. Okay, and let's define something about uh, all of the examples that we have seen, and then study in general. That's why we study, call them ring. That's how this definition came up. And then we study in general what is there in ring theory. Okay, and then as a particular case in one of each of these examples you can do. So what is the definition? So a ring R, now I am doing it for any abstract set. Okay, a ring R is a set with two law of composition or with two binary operation. I'm calling them by addition and multiplication, denoted by plus and multiplication, denoted by dot, okay, which satisfies the following condition. So what are the conditions? So with respect to addition, I'm saying that it should form a not only a group, it should form an abelian group. If you see, all the examples I have considered here are they are forming abelian groups. Okay. Shall we go to the next page?
Yes, ma'am.
Okay. What are the properties that R with respect to addition is an abelian group with, since it is a group, it will have an identity, and the notation to denote the additive identity is 0. Second says that multiplication operation is associative. That means what? A dot B into C is same as A dot B into C for all A, B, C in R. Third property says that there exists one element that I am denoting by 1 in R such that this is the multiplicative identity. Okay. And the fourth one is the distributive law. That means there should be some compatibility between these two operations, addition and multiplication. That is A plus B
Hello, ma'am.
dot C. Yes.
Ma'am, is it necessary that every ring has an identity?
Yeah, now there is a little bit controversy. So if you go into the book of Dummett and Foote, then they give the definition of the ring without considering the identity element. Okay, so these conditions is optional for them. This third condition is optional.
Okay, ma'am.
In Dummett and Foote.
Ma'am, David and Foote and Gallian and some other book are referring that identity, if identity include, then ring with unity.
With identity. Yeah, then we say ring with unity. That is true. But for this course, we will consider the definition to having identity only. Because if you go further, if you have the identity, then there are many nice properties which holds. Okay, so we will study in this course ring with identity only. That's why I have given in the definition itself that identity should be there. Okay, because in further, if you study say commutative algebra course, then also we assume all the rings to be with identity. Okay, and in algebraic geometry also, if you want to study, then also we assume the rings to be with identity. So for this course, I am assuming the ring to be with identity, but usually that is not taken care everywhere. For example, this Dummett and Foote, it's not there. Is it fine?
Yes, ma'am.
Okay. So now this distributive law says that it is same as P dot A plus B is equal to C dot A plus C dot B. Okay, this is for all A, B, C in R. Okay, so these are the four properties. If one set satisfies with respect to two operations, then we call it to be a ring. So for us, third property is not optional, it is compulsory. Okay, and if in addition you also have that AB is equal to BA for all AB in R, then we say that R is commutative ring. Then R is commutative ring. So this is also very important property, and there is this whole commutative algebra subject is developed on assuming the commutativity of the ring. Okay, so in this course also, most of the time we will assume our rings are commutative rings. Okay, because then many nice things happens. We get some nice structures in some of the cases and all. So now the examples, we have already seen the examples. Let me just go back. So all these are examples of ring. So this set of this is a ring. Okay. Then the polynomials is the set of all polynomials. This is a ring. Okay. So all these are examples of rings, and you might have already studied in linear algebra the concept of field. Have you studied?
Yes, ma'am.
So any field is a ring then?
Could you show
Yes,
previous
ma'am.
slide?
Sorry? Previous slide. Okay.
Okay, ma'am.
Yeah.
Ma'am, is it
Mm-hmm.
addition or multiplication? Ma'am, for a commutative ring, addition or multiplication?
Multiplication, because I am already assuming in the hypothesis that R plus is an abelian group. So with respect to addition, it is already commuting. Okay. So I'm assuming moreover that with respect to multiplication also it is commuting. Then only I am calling it a commutative ring. Okay. Fine.
Okay.
So now these are examples of rings, and so these polynomials I have defined first over any arbitrary. This polynomial here I have defined over the real numbers R. Okay, but you can define the same thing over any arbitrary ring R. So let me just say, so let R be a ring, and let us denote by Rx the set of all polynomials in X with coefficients from the ring R. So here this R is an arbitrary ring I'm starting with, and then I'm considering the set of all polynomials such that the coefficients are from this arbitrary ring R. Then you can see that this is also having a ring structure. Okay, so then Rx is a ring. Now, is Rx a commutative ring? Is this Rx a commutative ring?
No, ma'am.
Yes.
It depends on
If R is
our
commutative.
It depends on whether this R I have started with is that commutative or not. If your R is commutative, then only the polynomial ring will be commutative, isn't it? This is not the real numbers. This is just any arbitrary ring. Okay. So this will be commutative. So if R is commutative, then my Rx will be commutative.
Ma'am, here coefficients from where? Not real number then.
Is it okay? Can you say once again?
Ma'am, coefficient
Can you
from
say
not.
once again?
Ma'am, if coefficient from not real number, then from where coefficient coming?
Your voice was breaking.
Ma'am, coefficient from real number or any other set, which set? From which set?
Can you repeat the question?
Ma'am, coefficients from real number or
The
any other set, from which set?
The coefficients are from the ring R that I am starting with. Okay.
Okay, ma'am. Okay, ma'am.
Then what is the zero ring? The zero ring is only with the zero element, that is the additive identity. Okay. Consists of a single element 0. Okay. Now let me put a remark here. So let R be a ring in which multiplicative identity is same as additive identity. Multiplicative identity is same as additive identity. What can we say about the ring? What can I say about the ring?
It should be zero ring.
It should be zero ring because it should be then R is the zero ring. Then R is the zero ring. Why? Because if we start with say any element A in R, okay, then what will happen? Then A I
A is
can
equal
write
to
it
A into
as
1.
Yeah, A into 1, but 1 is equal to 0. That means 0 into A. But what is your 0 into A? 0 into A is equal to 0. That you prove. Okay. That means every element of R is 0. That means it is the zero ring. Okay. So there are a couple of things that I will leave you as an exercise. You try to prove. Should I go to the next page?
Yes.
Yes.
Okay. So the following proposition, which says that let R be a ring, then the following are true. First one, that if you multiply 0 with any element, then you will get 0. Second is minus A. Minus A denotes what? The additive inverse of the element A. So minus A dot B is same as A dot minus B, which is same as minus of AB. So what it says that the additive inverse of A, if you multiply it with B, is same as A multiplied with the additive inverse of B, and which is same as you multiply just A and B and consider the additive inverse of that. Okay. Then the third says that minus A into minus B is AB. And fourth one says that minus A is nothing but minus 1 into A. What is minus 1? Minus 1 is nothing but the additive inverse of the multiplicative identity 1. Okay. So most of the people confuse, let me put it as a remark, though it behaves in the same way. Here 0 and 1 are symbols or notation which denote the additive identity and multiplicative identity respectively. Is this clear? Don't think that this 0 is the number 0 or this 1 is the number 1. They are symbols to denote the, for example, if I consider the ring of matrices, in that case, this 0 denotes the 0 matrix where all the rows and columns are 0. And there, this 1 denotes the identity matrix, that is all the diagonals are 1 and remaining are 0. So these 0 and 1 are just the symbols to denote the additive and multiplicative identity of any abstract ring. Is it clear?
Yes, ma'am.
Yes, ma'am.
Now we have seen examples of rings and so on. So now let me give you some more definitions. So what is an unit element? So an element U, which is a non-zero element of R, is called a unit in R if there is some element V in R such that U into V is V into U gives you the identity. That means what? This is nothing but the multiplicative inverse. So the elements who are having the multiplicative inverse are called units. Okay. And the set of units in R is denoted by R cross. That is to denote the set of units. Okay. Fine. Now let us see example. Should I go to the next page?
Yes, ma'am.
Okay. So example. Can you tell me what are the units in Z?
1 and minus 1.
One.
Yes.
One.
Because this is the only two elements who are having multiplicative inverse. There are no other elements which has multiplicative inverse in Z, right? So the units in the ring of integers are 1 and minus 1. Okay. And what about the units in the polynomial ring over real numbers?
All non-zero constant polynomial.
Yes. Because only the non-zero constants are having multiplicative inverse. If you consider any linear or higher degree polynomial, you cannot get another polynomial such that it will give you the identity, right? So the units of Rx are non-zero constant polynomial. Okay. Now if I just replace this real number by any arbitrary ring, in that case, what will be the units?
Is equal to unit of ring.
Yes, will be the units of the ring. Correct. Now let us consider.
And
Yes.
in this previous example, Rx are non-zero constant polynomial only. And why constant polynomial are only units other than cannot and that?
So did you first understand why the non-zero constant polynomials will be units?
Because if we one upon that, then we can find
Yes.
in a number.
Exactly. But suppose if I have say 3x plus 1. Okay. If 3x plus 1 is a polynomial of degree 1, can I get some polynomial here such that whenever I multiply this with this, I will get the identity? Is it possible?
1 upon 3x plus 1 where x not equal to minus 1 by 3.
What is that you said?
1 upon 3x
1
plus
upon
3x plus 1.
3x plus 1. So if you multiply, what you will get?
No, 1 upon 3x plus 1. Whole thing inside.
1 upon 3x means you are saying 1 upon 3x is this you are considering?
1 denominator 3x plus 1.
1 denominator 3x plus 1. But is that a polynomial? Is this a
No,
polynomial?
no, ma'am. No, ma'am. Okay.
Then,
Okay, ma'am.
okay. Yeah. Yeah. Okay, fine. Now let us consider the other example. Suppose I have z quotient nz. Does it form a ring?
Yes, ma'am.
With respect to the modulus congruence addition and congruence multiplication, right? This is a ring. What are the units in z quotient nz?
With GCD 1 with n that are units,
Yes.
that element have inverse.
Yes. The units in z quotient nz are say m bar such that GCD of m and n is equal to 1. We have already seen this in the group structure as well, no? Because if this GCD is 1, then I can write it as this combination 1, and then when you go mod n, then you will able to write down this thing. Okay, is it clear or do I need to explain more? Is it clear or not?
Yes, ma'am.
Okay.
Clear, ma'am.
Okay, fine. Okay. So maybe my time is almost up. I will stop here today. I was thinking of taking one written exam on next week, Friday. Is it okay with you? The syllabus will be till the group theory, not the ring theory. Starting from the beginning till the structure theorem for finitely generated abelian groups. Is it fine? Give some response. Yeah.
Second week of March.
Sorry.
Can you take in the second week of March?
Second week of March, you are asking?
Yes, ma'am.
Yes, ma'am.
Okay. Let's